A long time ago, there were a great visionary to build a story that would inspire our generations to come. They left a legacy for timeless place to create a place beyond time, where history and heritage need innovation to inventory, where ideas take flight and lights ring down from above. This nation is an history and an art history to show us an everyday is an extraordinary point. It's here in the United Arab Emirates. This video is part of the Sustainable Architecture project, where we have 4 stops. In the first one, we spotlight the evolution of the sustainability thinking in UAE. Second is the case study building description. Third is the site and climate analysis. And last is the model simulation. Before the oil discovery, the country inhabitants lived in a traditional and simple lifestyle. They depended on sheep herding and date crops as their main income sources. The region's vernacular architecture reflected their cultural and social values. Citadel and forts are built for defense and use stone to make their thick walls. Mosques built near to the Bedouin homes are smaller than citadel while using same wall construction materials. Residential homes such as traditional tent and al-arish are used by the Bedouin as home shelter during winter and summer seasons. 3 main permanent homes recognized, which are islands, coastal, and the mountain homes.
Women are the backbone of the Emirati family life and social structure as they were participated in various aspects of life. They worked in agriculture, harvesting and marketing crops. They also have been involved in industries related to marine life and selling fish. In normal days, after lunch is considered a leisure time where women gathered and kids play fun games. Women's role in UAE has been developed rapidly after the oil discovery. They have started to be recognized in the sports world by giving them the chance to participate and compete against each other and against men to present their talent in sports. Emirati women have joined different sports like football and swimming sport and participated in various events and activities. Nowadays, sports education has been implemented in schools for both genders. Different ladies' clubs and institutions were provided in the country to encourage and support women's practice, such as General Women's Union in 1975, Sharjah Ladies Club in 1982, Dubai Ladies Club in 2006, Fatima bint Mubarak Ladies Sports Academy in 2010, Al Ain Ladies Club in 2014, Abu Dhabi Ladies Club in 2018.
The case study building is Al Ain Ladies Club, which is an ambitious project dedicated for ladies only and part of the Abu Dhabi Sports Council mission to ensure the provision of such integrated functional facility within the Emirate of Abu Dhabi. The club offers all relaxation and comfort facilities in which women in UAE can feel completely at home in public. With the diversified sports, recreation, and social activities, the club represents a vital addition of the community. The club is a complex building consisting of 4 floors and divided into 6 blocks. The project total area is more than 17,000 square meters and the gross floor area is 14,200 square meters. External openings accounts for more than 3,300 square meters. Thus, vertical glazing ratio is 36% and the horizontal glazing ratio is 3.2%. The external walls are basically lightweight concrete blocks with external stone cladding and internal dense plaster. There is no external shading devices applied to the current building design. The existing window glazing is double creel glass with aluminum frame. The project is located in Al Ain at Al Markhaniya sector and Marifia zone. It's situated alongside a major arterial road, Shakhbout bin Sultan, at the corner of street roundabout, hence providing easy users access. The temperature range chart for Al Ain shows that the city has hot climate during most of the year. Temperature range from 28 to 36 degrees Celsius, reaching a maximum of 48 degrees in the stifling month of July and August. The city experiences significant seasonal variation in the perceived humidity. The least humidity is on May 52% and the highest is on January 69%. The average hourly wind speed in Al Ain city experiences mild seasonal variations over the course of the year. From January to August, average wind speed is 3.5 meters per second. Northwest side experience higher wind velocities.
Moving on to model simulation, we will start with model setup, model validation, optimal orientation, passive design scenarios, and deciding the optimal design strategy. Starting with model setup, where weather data assigned for the project, annual solar radiation and shading calculations of the whole building run by SunCast module, and this is basically depends on Al Ain sun path throughout the year. The next step was to assign construction materials as per existing building based on data collected from the project's main contractor. The building awarded 2 Pearl rating certificate with defined wall, glazing, roof and skylight U value which were set in the model. Thermal conditions inputs have been set through Building Template Manager. Occupancy profile assigned for cooling system and people internal load as 50% daytime occupancy for non-holiday days. Design temperature for cooling set point is 22 Celsius while no heating system considered due to climatic conditions in the area. Relative humidity control kept between 30 and 70%. Air change rate profile follows cooling profile with minimum flow rate of 3.0 liter per second square meter. Infiltration gain set on continuously with external air maximum airflow 0.1 ACH. Internal gains were basically related to 2 factors. People 5% sensible gain 90 watt per person, latent heat 60 watt per person, and electrical lighting fluorescent lighting with domestic lighting profile.
To validate our model, 2 different software have been used, the IES and the eQuest. The energy consumption output from both programs compared against the actual electricity bills. The Apache simulation reveals that variance between the simulation output of the energy consumption and the actual measures is 3.8% using eQuest and 2.1% using IES. Since both results have less than 5% variance, then our model considered as a valid model.
To assess and identify the best orientation of the building in terms of energy use and heat gain, SunCast simulation was conducted for 8 different orientations, while the Apache simulation revealed that the south orientation is superior in terms of energy consumption.
Moving on to passive design strategies, which are related to the design features applied to the base case scenario. The first strategy is related to the skin thermal insulation, where 3 different scenarios apply to the base case scenario in order to test their usefulness in improving thermal performance and reduce the energy consumption of the building. The second strategy is related to improving horizontal glazing, where 3 different scenarios apply to the winning scenario resulted from strategy 1. Likewise, the third strategy, which is related to the sun shading system, have 3 different scenarios that apply to the winning scenario of the second strategy. For mitigation of heat transmitted through building facade, new insulation material proposed to enhance the thermal conductivity and to decrease the absorbed solar energy by outer wall surface. The material selected based on the available market in the country, starting with scenario 1, the thermal conductivity for external wall changed from 0.32 to 0.18. For roof, it was changed in scenario 2 from 0.29 to 0.14, and last for scenario 3, where the vertical glazing U value changed from 2.5 to 1.3. Comparing between all scenarios, the Apache simulation revealed that scenario 3 is the optimal scenario that achieved the lowest energy consumption. 6th of August was selected for the simulation as it's the hottest day. Comparing between all scenarios, the air temperature improved for most block of the building by almost 3 degrees. In terms of total number of hours where air temperature within the thermal comfort range, the number of hours increased significantly in scenario 1 and 3. As there is no notable difference in the solar gain, CO2 concentration and relative humidity between all scenarios, then we did not present the results here. However, to quantify the reduction in energy consumption and by considering the accepted Abu Dhabi distribution tariff, which is 29.4 fils per kilowatt hour, the table shows the annual reduction in the electricity bill and, more importantly, the reduction in CO2 emissions per year. According to the results, scenario 3, which is the enhancement of horizontal glazing thermal conductivity, is the winning scenario.
From strategy 1 analysis, it was noticed that Block B and Block F performed the worst in relation to energy consumption and indoor air temperature. This is due to the existence of roof skylight. Strategy 2 aims to introduce different scenarios to enhance their performance. Starting with Scenario 4, where the skylight thermal conductivity changed from 3 to 0.6. Scenario 5 reduced the size of skylight in both blocks as shown in this table. In Scenario 6, sun shading system added above the skylight. From the Apache simulation and by comparing the three scenarios with the winning scenario from Strategy 1, Scenario 3, it was noticed that Scenario 5 achieved the highest reduction in energy consumption. Air temperature in Scenario 5 reflect the best results. Thus, Block F reduced 9 degrees and Block B reduced 3 degrees. The total number of hours where air temperature within the thermal comfort range is the highest in Scenario 5. However, Scenario 4, 5, and 6 perform better than Scenario 3 in comfort level. Solar heat gain performed better in Scenario 5.
Flux daylight analysis conducted for Scenario 5 and Scenario 6 to assure that resizing the skylight or adding shading have no adverse impact on the lux and daylight factor. The higher the daylight factor, the more natural light is available in the room.
In terms of electricity bill reduction and CO2 emission, Scenario 5 performed the best among other scenarios. According to the results, Scenario 5, which is the reduction of horizontal glazing ratio, is the winning scenario.
The third strategy is to add sun shading device with the aim of controlling the solar heat gains in building by intercepting unwanted solar rays, especially during the overheated period, which is 6 August from 9 a.m. to 4 p.m. The exterior shades design in this section will shade windows completely during these hours.
Starting with Scenario 7, overhang added to the south face of the building with ideal eave depth of 2.45 meter. In Scenario 8, vertical fence added to Block B, E, and F with 4 meter height and 40 cm thickness. However, in Scenario 9, combination of overhang and fines added to Block B and Block F. The Apache simulation for Strategy 3 reveals that Scenario 9 performed the better in terms of energy consumption among other scenarios and compared with the winning scenario of Strategy 2. In terms of air temperature, Scenario 9 performed the better between other scenarios. The number of hours within the comfort range in Scenario 9 increased significantly. However, the comfort zone for all scenarios are achieved. For the solar heat gain, the Scenario 9 performed the better. For the sensible cooling load, Scenario 9 performed the better. In conclusion, the optimal strategy is to enhance the vertical glazing U value as per Scenario 3, reduce skylight radiation as per Scenario 5, and add combination of shade system as per Scenario 9.
Fountains are delightful scenarios and can provide refreshing surrounding atmosphere because of the cooling and the humidifying effect of water droplets. A model built using SC-Stream to quantify the thermal effect of fountains through transient analysis for 30 minutes of CFD simulation. Structure mesh employed for computational domain and boundary condition of weather gathered from climate consultant. As the time limit of the CFD simulation is 30 minutes, the time set in our model is from 12 p.m. to 12:30 p.m. By comparing the result of point surface temperature before and after adding water fountain, it shows an enhancement in external temperature from 44.96 degrees Celsius to 40.21 degrees Celsius at 12:30 p.m. From the model simulation, comparison of the relative humidity before and after adding the water fountain is presented. Global solar radiation and same to the magnitude of the velocity. Finally, 1 meter above the ground of the plant temperature.